All right, so in the previous videos, we talked about why we were interested in power series in the first place. So they come as a way to integrate functions that we hadn't integrated before, and a way to write down exact values and approximations of functions that don't have a closed form. And also we can think about power series as an extension of linear approximation. And so when you have these power series, which are basically like infinite polynomials, and you plug a number into those, you end up with something called a series, which is an infinite sum of numbers. And so we had talked a little bit before about the integral test and how to run that test. And from that, we had derived that this series, 1 over n squared, converged. And we proved that using the integral test. So something we can look at is we can use that knowledge to compare that to other tests. So we can use things that we know from the integral test, from geometric series and p-series and so on, and compare those to other functions. And so if I looked, say, at this series, I can take that series and I can compare it to, so I can look at the highest powers of n here are going to be the dominant terms in the numerator and denominator. And if I reduce that, I get 1 over n squared. So what I'm saying is that this series here ought to behave like the series 1 over n squared eventually. And so what we can do is we can compare do a term by term comparison of these two series and see what I get. So we can say we will compare the given series with the convergent series (1 over n squared). And so how do these terms compare? So if I look at n squared over n to the fourth plus n plus 1, how does that compare with, well, I'm going to write 1 over n squared this way. I'm going to write it as n squared over n to the fourth. So which of these is bigger? Well, let's think about it. The left-hand side here has a bigger denominator. So when the denominator is bigger, that means the entire fraction is smaller. So since this has these extra positive bits here, I know that whole thing is smaller. And I'm saying that those things are positive because I'm plugging in positive n's. Remember, my n goes from 1 to infinity, so I'm only dealing with positive n's, and so n plus 1 is always going to be positive if n is positive. And so the denominator here on the left-hand side is going to be bigger than the denominator on the right-hand side. The numerators are the same, and so that means that the right-hand side is going to be bigger. So what we have here is that I have a series. The series that I'm given here, this series, is going to be smaller than, each term is going to be smaller than the series n squared over n to the fourth. So since the given series is smaller than, what I've shown is that every term is smaller than the convergent series. Then the series, the given series will also converge. Why? Because what does it mean to converge? Converging means that it adds to a finite number, right? That's what that means. And so if I have the series 1 over n squared adds to a finite number, and I know that all of the terms of n squared over n to the fourth plus n plus 1, I know that all of those terms are smaller than the terms of 1 over n squared, then it should also add to a finite number that is smaller than the finite number that 1 over n squared is going to add to. So that is called the direct comparison test. So if I have a series that's smaller than a convergent series, then it will converge. And similarly, if I have a series that's bigger than a divergent series, then it will diverge. But we have to think about what happens if our sign here is not going the correct direction. So let's look at a related series. So let's look at, I'm going to change this up here. That's an infinity. So if I do 1 over n squared over n to the fourth minus n minus 1, well, what happens then? So we will compare the given series to the convergent series over n squared. So if I compare those, I get n squared over n to the fourth minus n minus 1, and I'm going to compare that to n squared over n to the fourth. So I'm just really looking at those dominant terms here to do this comparison. Well, what I have is that the numerators are the same, but the denominators are different. The denominator on the left-hand side is smaller, which means the entire fraction is bigger. Okay, and so what does this say? Since the sign is going that direction, what does that mean? Well, I have a series that is bigger than, term by term, is bigger than 1 over n squared, which is a convergent series. So if it's greater than a convergent series, what does that tell us? Well, it tells us nothing. It just means that when I add that infinite sum, it's going to be greater than some finite number. Well, that doesn't tell us if it's finite or infinite. We don't know anything from that. But we expect that this series will behave in the same way as 1 over n squared, regardless of the sign going the wrong direction. And so when that happens, we can't do a direct comparison test. We have to do something called a limit comparison. Okay, so if the sign goes the wrong direction, we can still use our comparison, but we have to do a limit comparison. And so what we're going to do is we're going to say the limit as n goes to infinity of this, well, we could do it either way. We can say, that one over this one, or vice versa. So I'll just do 1 over n squared over n squared over n to the fourth minus n minus 1. And so let's work out the algebra on that. And so what we end up with is the limit as n goes to infinity of 1 over n squared times n to the fourth minus n minus 1 over n squared. So we get the limit as n goes to infinity of n to the fourth minus n minus 1 over n to the fourth. And so if you remember from Calculus 1, we can evaluate these by looking at the leading coefficients, and I see that they're both in n to the fourth term, and the coefficients in front of each of those is 1, and so that limit is going to end up being 1. And so since that is a finite number, that tells me that this ratio of the two eventually becomes 1. In other words, as n gets bigger and bigger, these two series are going to act more and more alike. And so that means that, so when I get a finite number from this limit comparison, that is telling me that the series are going to behave the same. So that means that since the sum of 1 over n squared converges, we know that this sum n equals 1 to infinity of n squared over n to the fourth minus n minus 1 will also converge. And similarly, if we were doing a limit comparison to a divergent series and we got a finite number, that would just tell us that they're going to act the same way. So if we get a finite number there, then that means that the thing we're comparing to is going to act the same as the given function.